Okay, the Miller family is raising puppies and they need 3 kennels. They decide to build a rectangular kennel with 50 feet of fencing, and they divide that kennel into 3 equal parts. Okay, so that gives you 3 different kennels. Find the dimensions that would maximize the enclosed area. So we're looking for max area, and that's how it would start. Okay, so let's go back to our diagram for just a second. I've got this side and this side. Okay, that looks like the longest side to me, so I'm going to call it L. And I also have this side of the rectangle and this side of the rectangle, so I'm going to call that W. But I also notice that this is the same length and this is the same length, so this is also W, W, and W. Now, that's what my picture looks like, and there are my variables. The first thing we had to do, of course, was talk about maximum area, and I'm talking about the area of the rectangle. Now, so there's a lot of stuff going on in this picture, but when we're talking about the area of a rectangle, that's just this green region right here. So the area of any rectangle would just be length times width. Alright, so what I have to do is I have to change the area function to only having one variable. So I need to use my other facts. The other facts that were given were that you had 50 feet of fencing. Well, if you look at your picture up here, there were 4 W's and 2 L's, and that's how much fencing that you used. There were 4 W's and 2 L's. Now, at this point, it doesn't matter which letter you change it to. I've been solving for L every time, so I'm just going to continue in that manner. So 2L would equal 50 minus 4W. To solve for L, I'll divide both sides by 2. So L would equal 25 minus 2W. So over here, you'll go to your optimization formula. Length is 25 minus 2W, and W, of course, is W. Okay, this is your optimization formula. What you're going to do with this green formula is set it equal to 0. Okay, so I just misspoke. What you're going to do with this formula is take the derivative of it and then set it to 0. So the derivative of this formula is 25 minus 4W. 25 minus 4W. We're going to set that function equal to 0. I'll move the 4 over, divide by 4, and W would equal 6.25. Okay, that's my critical number. Now, let's talk about the restrictions. I know that W is the distance, so it has to be positive. I also know that the length has to be positive. Well, the length is 25 minus 2W. That has to be positive. So a negative 2W would have to be greater than or equal to a negative 25 when we move that over. I'll divide both sides by negative 2, and when I do that, it flips my sign. So W is less than or equal to 12.5. So the restrictions on W, when we optimize over the domain, W has to be between 0 and 12.5. Okay, let's go back to our optimization formula over here. My critical number was W equals 6.25. My endpoint of my domain is when W equals 0, and also when W equals 12.5. So I'm going to plug these 3 values into the area function to see which one gives me the maximum area. So area would be 25 times 6.25 minus 2 times 6.25 squared. Okay, so let's figure out what that would be. Okay, so there's one area value. Then we can plug in 0. Okay, when I plug in 0, I get 25 times 0 minus 2 times 0 squared. Okay, so that would equal 0. Okay, I can also plug in 12.5. So area would equal 25 times 12.5 minus 2 times 12.5 squared. Now, if you put all that in, you're going to get that the area is 0. So remember, we're looking for maximum area. So your maximum area would be that 78.125, and that 78.125 occurred when the width was 6.25. Now then, it asks you for the dimensions, so we also need the length. So go back to the length formula that you see in the middle. Length would equal 25 minus 2 times 6.25. So that would equal 25 minus 12.5. So that means your length for maximum area would be 12.5. And that is your answer.